Hi, my name is Dulloor. I'm from Intel Labs, and today I'm going to present our work YAT. YAT is a validation tool that we built to test and validate persistent memory software, and this work was done in joint collaboration with the authors listed here. So what is persistent memory? Just a brief introduction. It is non-volatile memory attached directly to the CPU, so the software can access it directly using regular load store instructions, and as regular cacheable memory. And it is also preferably based on emerging NVM technologies such as STD-RAM or RRAM or PCM, and whose performance is comparable to DRAM. Now, there are many differences between traditional storage and persistent memory software, and we are going to look at some of the key differences with particular emphasis on consistency, which is important to this paper. So traditionally, the storage has always resided in a different address space from memory. And for software to access the storage data, it has to first copy over the data to the memory, to the DRAM, and then access it. Similarly, when it wants to make the data durable, it has to explicitly flush the data back to the storage device. So software is always in control of when and how the data becomes durable. But at the same time, there are all these inherent overheads in doing address translations, copies back and forth, and so on. Enters persistent memory. So with persistent memory, the storage is in the same address space. And in fact, persistent memory is part of the CPU's memory hierarchy. And research has shown that it is possible to tailor your software to the capabilities of persistent memory and achieve huge performance gains. PMFS, which we built, and BPFS from Microsoft Research, Nemosini, and NVHeaps are examples of such software. But there are some challenges too, and challenges that are more specific to the consistency. So for one, software is no longer in control of when and how the data becomes durable, in the sense when the dirty data gets pushed to the persistent memory. This is due to the fact that the evictions from the CPU caches is managed by the hardware. And also, software is no longer in control of the ordering of the writes to the persistent memory, because the reordering can happen in the core or in the memory controller or anywhere along the line. So these things make consistency a little tricky, even more tricky than usual. And we face the same challenges when we built PMFS, and we realized the importance of a tool that can help us test and validate persistent memory software. So we built YAT. YAT is a validation framework that we originally built for PMFS, but the design and the implementation were generic enough that we were easily able to extend it to test other persistent memory software. So before I get into the specifics of YAT, let me give you a brief overview of the ordering and durability model of, that we assumed and that we proposed. So consider a piece of software that wants to perform two sets of writes, W1 and W2. The software wants to make all the writes in W1 and W2 persistent or durable. The software also wants to make all the writes in W1 persistent before any of the writes in W2. This is a very common pattern to ensure consistency in software such as file systems and databases and so on. But as I just mentioned, it becomes complicated in persistent memory because the reordering and evictions are not in software control anymore. So what we did is we proposed a very simple model that you can use to achieve the desired ordering and durability, which depends on the disciplined use of two operations. The first operation is an existing instruction, CLFlush instruction, which allows the software to flush the data from the CPU caches. And the second operation, or the primitive, is the PM write barrier primitive that we proposed. And it's a very simple primitive. It allows the software to, it just guarantees the software that on the completion of a PM write barrier operation, all the dirty data that was already out of the CPU caches is just made durable by being pushed to the power failsafe buffers. Now let's take a look at the software flow that I just described with these two instructions in place. So the software wants to perform all the writes in W1 before any of the writes in W2, right? So the software performs the writes. Data could be sitting in the CPU cache, in the memory controller, or in the persistent memory. We don't know. But the software can explicitly flush this data to push them out of the caches, and then issue a single PM write barrier to push the data all the way to the persistent memory. Similarly, with the writes in W2, it can follow the same technique or the same steps to make the writes in W2 persistent and achieve the desired ordering and durability. This is a very simple model, and there's a reason why we chose to go with such a simple model, which is described in the paper. But there are several things that can go wrong here. For one, the software is now responsible for keeping track of all the dirty data in the CPU caches and explicitly flushing it. And it is possible that we might miss or misplace a CL flush, and all of a sudden the ordering breaks, right? It is also important that the software uses PM write barrier in a correct manner, and a missing or misplaced PM write barrier can break ordering or durability. And to make matters worse, even if the software actually misses or misplaces a CL flush or a PM write barrier instruction, it might not necessarily show up as a problem immediately, because, as I mentioned, the ordering, the reordering and the evictions is done by the hardware, and we might have just ended up with one possible ordering where things just worked fine. So to test the PM software, it is not sufficient to just test for one memory ordering, but it is important to test for all the possible memory orderings as allowed by the architecture. So the validation of PM software is a little more tricky and difficult than usual. I'm not saying it's a completely new area or something, but it's a little more tricky and difficult than usual. So we built Yeth. So I'm going to briefly introduce the goals that we had in building Yeth first. So the first goal was obviously that we wanted to test for the correct use of CL flushes and PM write barriers and so on, which is important, as we have just seen. We also wanted to test for all the possible memory orderings as allowed by the x86 architecture. We wanted to simulate a large variety of failures, both power failures and software failures, and test for consistency in each of these failure conditions. And we wanted to exercise the recovery code for each of these failure conditions. Recovery code is not exercised as often as your regular application, and for a good reason. So it needs to be tested as thoroughly, or even more thoroughly, because it doesn't get enough coverage. And finally, Yeth, when it indeed finds a bug, we wanted to provide the developer with sufficient diagnostic information to help them in debugging the problem. And this diagnostic information could be in terms of information that is inserted by the Yeth itself, or some application-provided hints and annotations and so on. So let's take a look at the overall design of Yeth now. Yeth broadly consists of two phases, a record phase and a replay phase. In the record phase, we simply run the PM application with Yeth, and Yeth sits in the background recording all the operations that can possibly alter the state of PM. For us, it includes all the write operations, the CL flushes, write barriers, fences, and any other application-specific information such as annotations and hints and so on. And the output of the record phase is a trace of the PM software execution, the actual test that you want to perform. And that is input to the next phase, which is the replay phase. And the Yeth replay phase is the more time-consuming phase, and it loops over several sub-steps. The first step is to actually segment the input trace into multiple segments delineated by the PM write barrier operations. And each segment is then fed to the reorder step, which takes as its input a segment and an initial base PM state. And then the reorder takes this segment and generates a set of combinations. And these combinations are nothing but all the subsets of all the operations in the segment and all the permutations of these subset of operations. So it's exponential. Then the output from the reorder step is a combination, and that is fed to the replay along with the initial base PM state. The replay phase initializes the persistent memory to a known base PM state, and then just simply replace the operations in the combination. And then Yeth invokes a failure. And after invoking a failure, and the invocation of failure is configurable, by the way. After invoking failure, it automatically invokes the recovery code in the persistent memory application. And after the recovery, it invokes the verification tool to test for the consistency of application data. So as you can see, there are only three pieces of information that the persistent memory application itself needs to provide. The application itself, a method to invoke the recovery mechanism in the persistent memory application. For instance, in case of PMFS, it was just remounting the file system. And the third thing is a verification tool, which lets us test for the consistency of the persistent memory application data. And again, in case of PMFS, it was something similar to FSCK. Now, there, as you just saw, the number of combinations that come out of the reorder step is exponential in terms of the number of operations, and it can quickly grow to a very large number. So yet does provide the obvious option to cap the number of combinations to a predefined threshold. But in addition, yet also implements several optimizations to further prune the combination space. And these optimizations fall in both transparent and non-transparent categories. That is transparent or non-transparent to the applications. In the transparent techniques, as an example, yet makes use of the memory ordering constraints of x86 to prune a large number of combinations. Let me give you an example. The writes in the Intel process, it is guaranteed that the writes to the same cache line are never reordered. So when yet indeed encounters writes to the same cache line, it makes use of the constraint, and it just simply skips the reorderings for them and prunes the combination space. An example of a non-transparent technique where the application can help in skip some of the reorderings is many of the applications, as you know, have a zeroing operation, a memset-like operation where they are just simply zeroing a large memory buffer. And in operations like this, there is not much value in terms of testing to reorder the operations within a single mem copy of 4K or something like that. Remember that we are seeing the writes at a very fine granularity, probably at 8-byte granularity. So the reordering grows, the number of combination grows really fast. So for such operations where there's not much value in reordering, application can provide the hints and to skip the reordering for those operations, and yet does that. We also noted that the replay phase in the yet framework can be easily run in parallel. We started a base PM state, and then we replay the operations. So you can test for multiple combinations at the same time. So we did that. We implemented a multi-threaded version of yet, which lets us test for several combinations at the same time and use all the available cores. And although we haven't implemented any distributed form of this, it is easy to see how we can do that. So yet can be implemented in multiple ways. In the paper, we described a virtualization-based approach, which uses our internal type 1 hypervisor to implement both the record and replay phases. We found this virtualization-based approach to be very powerful and very useful in testing the Ring 0 PM software, such as PMFS. But at the same time, if you are just interested in testing, and by the way, you can find the details of the implementation itself in the paper. And at the same time, if you really want to test only the applications, the Ring 3 applications, there might be additional setup overhead in getting all this virtualization-based yet going, right? So what we did was we also ported the yet logic to use a binary instrumentation tool called PIN, which is a publicly available tool from Intel. And it was surprisingly easy to port yet's logic to use PIN, at least the record phase. And the replay phase, of course, depends on your application's complexity. And and we found this PIN to be very useful in testing a lot of application software. And this was supposed to be a short presentation. So, so with this, I would like to conclude the presentation with these points. So the persistent memory is actually a huge paradigm shift. And research has shown that it is possible to gain huge performance improvements by tailoring your software to persistent memory capabilities. But we also found that consistency is extremely tricky and easy to get wrong with persistent memory. And it's also difficult to know when we actually got it right. So we need validation tools to test and validate persistent memory software. And yet is one such tool. Yet helped us find many bugs in PMFS, and we also, and you can find the details of this in the paper. And we also see several possible potential extensions to yet, and we encourage the community to tackle these challenges. Thank you.
From Samsung Electronics.
Hi.
I was wondering why you are based on internal hypervisor rather than open source hypervisor like Gen or KVM.
Well, there's only one reason, because the guys in my team, including me, are more comfortable with that. We built this hypervisor way before the Zen and KVM, and it's It's not actually like a full-fledged hypervisor. It's more like a monitoring hypervisor. You can run only one single guest, but you can easily monitor whatever is going on in the guest at very low overhead. There's no DOM 0, there's none of that nonsense. So, yeah.
Ashwin Goel, Toronto. Perhaps this is addressed in your previous paper. I was just wondering whether you ever use your flush and barrier primitives. In your slides, you show them being used one after the other. Do you ever use them independently? In other words, why do you need both of them?
The flush and barrier?
Yeah.
Well, so...
I mean, in this example, it seemed to suggest you need to use both of them in exactly that order. So why don't you have just one?
Well, this is a very simple example. I was just trying to show the simplest example, right? But, so at the high level, this is what CLFlush does. It just guarantees that the data is pushed out of the CPU caches.
Right.
It could still be residing in your memory controller, anywhere along the line, and it might not have reached your power fail-safe buffers. So the PM write barrier is the actual instruction or the actual primitive which guarantees that the data is moved even out of the integrated memory controller, for instance.
So here's the problem. What if you don't issue the flush and you just issue the barrier? What happens?
Then it is the PM write barrier only guarantees that the data out of the CPU caches is made durable. So the writes in W1 will not be durable. So you have the writes in W1, and then if you don't flush it. Yeah, okay.
Actually, had one more question. I was curious. Much of the problem you're trying to solve is due to this huge asynchrony that the modern memory system provides for memory operations.
Yeah.
Do you have a sense of whether this is going to be the case for persistent memory, or whether it might be that future CPU architectures will have a more synchronous memory model for persistent memory regions in particular?
Yeah. I can only probably talk about one specific example in this case because I haven't thought about all the options, right? So it is an option today to use either write-through mappings or write-back mappings, right? Now, one could imagine that you could extend write-through mappings to enforce strict ordering for all the writes all the way to the persistent memory. But you have to look at the performance of that. It really sucks. The performance is, I'm sorry for the words, but the performance of that is really horrible. So there's a good reason to continue using a more write-back cacheable kind of thing going forward. And particularly considering the fact that these emerging technologies are expected to have really bad, considerably bad write performance. So with write-back mapping, what happens is if you're doing writes, you don't actually see the latency of these underlying devices. It's a posted write. You just post to the cache and you move on. You see it only at the point when you're actually issuing the write barrier. So.
Michael Condit, NetApp. So isn't all of this complex stuff that you're trying to fix here, isn't it just a result of the danger of power failure? That's the only thing, that caches might not get flushed on power failure?
Yeah.
Isn't the right way to fix this just to make sure that caches always get flushed on power failure?
So that is interesting. And I think you know about the previous work from Microsoft Research, which was talking about this whole system persistence, and some recent work from the ISCA last year, or ASPLOS last year, which was talking about similar techniques. And it is probably easy to think of these things in a client system where things are more controlled. And even there, the things become more complicated when you think of all the possible I/O devices and I/O state and so on, which you have to decide how we can get all the I/O device and everything else into a quiescent state as well.
But
Okay.
this isn't, these aren't I/O devices on a PCI bus. It's just, we just need enough super caps to flush a few megabytes of
But those
cache to
states-
physical RAM.
But those states could be interdependent. Those states could be interdependent. And that's one example. But I'll give you another example where you still have to worry about ordering to some extent, in the sense that the cache flush that you do, the CPU cache flush that you do is going to be more or less a dumb operation. You're just going to flush everything that is in your CPU caches, okay? And assuming that you're able to do that, when you come back up, you don't want to end up with a split brain kind of thing where some of your OS state and some of your OS data is current, and the rest of it is suddenly it doesn't make any sense. So I mean, it is. I understand it has value. But I was coming more from what is more useful in the server space, where you have multiple memory controllers and a lot of things going on, and it is difficult to even think of how we can always guarantee that the flush happens as desired.
Okay.
So,
Great. Let's thank Dulloor again.
yeah, thank you.